പിന്നെ ശ്രദ്ധിക്ക, നീ ലീവ് ചെയ്യുമ്പോഴേ
അല്ല ഇപ്പൊ ഞാൻ റെക്കോർഡ് ചെയ്തു എന്നിട്ട് ഇപ്പൊ പോസ് ചെയ്ത് നോക്കട്ടെ ഒരു ഇത്
ഇപ്പൊ പോസ്റ്റ് ചെയ്തോ.
We are very pleased. Today we are very pleased to inform that we are joined with us Dr. Himanshu Kumar. Dr. Himanshu Kumar is currently a postdoctoral fellow in Cleveland Clinic, USA, where he works at intersection of neuroscience, biomedical engineering, and machine learning with a primary focus on epilepsy research using stereo electroencephalography. He has earned his PhD in biomedical engineering from IIT Madras, where his dissertation focused on analysis and classification of EEG signals for emotion recognition using audiovisual stimuli. His doctoral research integrated traditional signal processing techniques with advanced machine learning methods, including explainable AI to decode emotional states from EEG dynamics. Dr. Kumar holds an integrated BTech MTech degree in biomedical engineering from IIIT Allahabad, where he was honored with a medal for academic excellence. He has received prestigious international fellowships, including that Binational Research Fellowship with an Advanced Research Opportunity Program. Kumar has published in several high-impact international journals and has presented his work at major global conferences. With his expertise in EEG and stereo EEG analysis, brain connectivity, nonlinear signal dynamics, multimodal data fusion, and AI-driven diagnostics, he is dedicated to developing advanced analytical tools for digital brain health and clinical neuroscience. It is indeed a great pleasure to invite you, sir. He'll be taking a session on exploring brain dynamics, detecting emotion and impulsivity for digital health. Welcome you, sir.
Thank you, Surya. Am I audible?
Yes, sir.
Yes, sir.
Yeah, so good morning, everyone. I'm Himanshu Kumar. I'm a postdoctoral fellow at the Neurological Institute, Cleveland Clinic, United States. Today, I'll be discussing exploring brain dynamics, that is detecting emotions and impulsivity for digital health. I have divided this talk into three major sections. First is emotional analysis, second is impulsivity detection, and the third one is integration of AI-based approaches for enhanced digital outcomes. The presentation will focus on neuroscience and its application in digital health. The topic combines multiple disciplines, that is neurology, psychology, and digital health. The mention of brain dynamics suggests a focus on how the brain changes and functions over time. Detecting emotions and impulsivity implies the use of neurological data to identify psychological states. The digital health aspect suggests practical applications in healthcare technology. Now, let's talk about mental health. In this first slide, I am talking why emotional studies are crucial for understanding conditions like autism, depression, and Alzheimer's disease. As you can see on the slide, these conditions affect significant portion of our population. We can see that 11% of children between 4 to 17 years have been diagnosed with ADHD, which often co-occurs with the autism. 1 in 5 students have diagnosed mental health disorders, and 1 in 4 young adults will experience depression before the age of 24. For our older population, 1 in 9 people over 65 has Alzheimer's disease, and notably, women are twice as likely to suffer from depression and anxiety compared with men. So why study emotions and impulsivity in these conditions? Because they are fundamental to how these disorders manifest. In autism, this difficulties with emotional regulation and recognition create social challenges. Impulsivity can lead to overwhelming sensory-rich environments. With depression, emotional dysregulation affects how people process negative experiences, while impulsivity can heighten suicide risk during severe episodes. In Alzheimer's, as cognitive function declines, uh, emotional processing changes dramatically, sometimes leading to impulsive behaviors that weren't present before. By studying these emotional patterns, we can develop more targeted interventions that addresses the core mechanisms of these conditions rather than just the their symptoms, potentially revolutionizing treatment approaches. So, before talking about the fundamentals of emotional processing, we have to understand what is emotion. Emotions is fundamental intellectual capacity of humans characterized by perception, attention, and behavior. The word emotional itself reveals much about its nature, dating back in 1579 and adapted from the French word émouvoir, meaning to stir up, and stir up is certainly does. In the slide, you can see emotions like happiness, sadness, and disgust creates complex interconnected responses across three key domains. That is, physiologically, emotions triggers measurable body changes. See how happiness increases heart rate and bronchi dilation, while sadness decreases these same functions. Disgust creates its own unique pattern, including increased skin temperature, but decreased bronchi dilation. Behaviorally, each emotion has distinctive facial signatures. Happiness raises the cheeks and exposes teeth, while sadness creates downturned lip corners and raised eyebrows. Disgust manifests through raised upper lips and nose wrinkles. Uh, Experientially, emotions profoundly affect our cognitive functions. Happiness enhances decision making, social interaction, and creativity, while both sadness and disgust tends to diminish these capacities. uh, what makes emotions so complex is precisely these interdependencies between subjective experience, physiological responses, and behavioral expression. This three-dimensional nature of emotions explains why they are so powerful in shaping our mental health, and why understanding emotions and emotional pattern is crucial for treating conditions like depression, autism, and Alzheimer's. Now, coming to the complexity of the emotions. Complexity of emotion has humans have a remarkable complexity and the sophisticated system that underlines them. We can see on the slides that emotions operate through a multi-layer process with three key components. Component A represents changes in our central nervous system, the neurobiological foundation of the emotion. This includes physiological symptoms, motor expression, and tendencies that occur largely below our consciousness awareness. So we don't know what is happening at this level. Now, talking about component B, it involves our verbal accounting of feelings with partial consciousness, that middle ground where we become aware of emotional states through unconscious reflection and regulation. Now comes the component C. Component C represents the full verbalization of emotional experience, the conscious articulation that forms the basis for existing emotional measurement scales, and the zone where valid self-reporting becomes possible. This is the part or component where we understand what we are experiencing, and somehow we can manage and control it. You can see the bottom portion illustrates the relationship between emotional components through two complementary models. On the left, we see emotion as a hierarchical systems, beginning with basic monitoring of an internal state, progressing through communication of reactions, preparation of action, regulation, and culminating the evaluation of events. The central diagram shows how different neural systems, that is central nervous system, autonomic nervous system, and SNS, coordinate specific emotional functions like monitoring, action, execution, support, and information processing. On the right, the flow of action moves from cognitive process through neurophysiological responses and motivational states to motor expressions and finally subjective feelings. Understanding this complexity is crucial for developing effective interventions in mental health conditions where emotional processing is disrupted. Now, coming to the existing scales of emotions, building on an understanding of emotional complexity, we can explore the four major framework that researchers use to measure and understand emotions. First, the discrete model identifies six primary emotions that appear universally across cultures, that is anger, disgust, fear, joy, sadness, and surprise. This model suggests that emotions have distinct neural signatures and facial expressions that are biologically hardwired. The dimensional model takes a different approach by plotting emotions along continuous scales of arousal, valence, dominance. As we can see in the circumplex model and the cubic diagram, this allows us to understand emotions as related states rather than as separate individual entities or categories. For instance, anxiety and excitement shares high arousal but differ in valence. The appraisal model focuses on emotions as a process rather than states. This framework shown in the bottom left examines how our cognitive evaluation of events triggers emotional responses. It illustrates how same situation can produce different emotions in different people based on their appraisal patterns. Finally, the dynamic model emphasizes that emotions unfold over time through interconnected components. As shown in the bottom right, this includes the initial event, multi-level appraisal, physiological responses, multi-mental representation, and then categorization through verbal labeling. These complementary frameworks helps researchers to design more nuanced measurement tools for emotions, which is particularly valuable when studying conditions like depression and autism, where emotional processing differs significantly. Now we'll talk about the dimensional circumplex model of affect. The Russell circumplex model of affect, one of the most common used approaches to understand emotions. What makes this model so powerful is its elegant simplicity. Rather than treating emotions as a separate category, Russell proposed that all emotional states can be mapped using two fundamental dimensions, that is valence and arousal. Valence represents how pleasant or unpleasant an emotion feels, while arousal represents the intensity or the level of emotional experience. As you can see in the circular diagram, these two dimensions create a continuous space where any emotions can be precisely plotted. The model consists of four distinct quadrants. In the upper right, we find a high arousal positive emotions like excitement and elation. The upper left contains high arousal negative states like stress and anxiety. The lower right features low arousal positive feelings such as calm and relaxation. And the lower left shows low arousal negative states, including sadness and boredom. This, this dimensional approach offers a significant advantages for mental health research. For instance, in depression studies, we can track how treatment gradually moves on person's emotional state from sad depressed region towards a more positive balance. For anxiety disorders, we can monitor shifts from the tense nervous quadrant towards lower arousal states. The circular nature of the model also helps explain how emotional states blend and transition into one another. Unlike the traditional way of analyzing emotions, where we consider the emotions as a discrete state, which is not as natural as we see in the circular nature of the Russell circumplex model of emotions. Now, after understanding what is emotions, how to quantify it, how to make it into a more quantifiable study, I'm going to talk about how to analyze emotions. So, how do actually you measure emotions? You can see in the slide there are two complementary approaches. First one, we have a non-physiological measures. These includes facial expressions through techniques like facial active action coding systems, then examining speech patterns for emotional indicators like pitch, tempo, then studying body gestures such as posture and movement. While these methods prove rich in behavioral data, they come with an important limitation that they can be consciously controlled. This creates a significant challenge since subjects may intentionally or unintentionally mask their true emotional states, meaning that the emotions we observe may not be genuine. On the right hand side, we can see the neurophysiological measures that provide objective data directly from the body systems. So EEG captures electrical brain activity associated with emotional processing. Heart rate variability, HRV, reflects how emotions affect autonomic nervous system. EMG measures the muscle activity tied to emotional expression like facial EMG. And then EDA, that is electrodermal activity, it detects subtle changes in skin conductance linked to arousal or valence states. The major or key benefit of this physiological approaches is that they are largely outside the conscious control, and it makes them a more reliable indicators of genuine emotional states. Now, coming to the studying emotions, as we have talked about, the physiological techniques is better as compared to non-physiological techniques. But the physiological way has also two types. That is, one through neuroimaging. That is, we study the source of the emotions, where the emotions is originating. That is through the brain, and other physiological techniques. neuroimaging methods gives us a direct window into the brain's emotional activity. We can see the functional magnetic resonance imaging, that is fMRI, measures blood oxygenation and flow, and it shows which brain regions activate more during emotional experiences. EEG, that is electroencephalogram, captures electrical activity within a high temporal resolution, means with a high millisecond precision, we can capture the emotional activity. It helps in revealing the timing of emotional processing. The magnetoencephalography, that is MEG, detects magnetic fields generated by neural activity. The positron emission topography, that is PET, tracks metabolic activity through radioactive traces. The strength of these techniques are considerable. Like, this is a direct measurement of brain activity. It has excellent spatial resolution with fMRI and PET, and superior temporal resolution with EEG and MEG, and a comprehensive whole brain coverage. However, they come with the significant limitations like high cost, limited mobility, artificial testing environments, and complex data processing requirements. On the right, we have a physiological techniques like HRV, which measures the heart rate variability that is linked to uh, emotional regulation, eye tracking and pupillometry that reveals attention patterns and arousal, EDA, that is GSR, that detects subtle changes in skin conductance during emotional responses. These methods also offer some really distinct advantages, like they are cost effective, they are portable, they are non-invasive, it can be applicable in real world setting and allow for continuous monitoring. However, they provide only indirect measurement of emotional states, which can need multiple interpretations and are sensitive to environmental factors and lack cognitive specificity. Now, after understanding the emotions and shifting our focus from emotion broadly to a specific behavioral trait that impacts mental health, that is impulsivity. Let's understand what is impulsivity. So impulsivity is a fundamentally it is fundamentally characterized by action without thinking and with diminished sensitivity to negative consequences. You can see in the diagram that this process follows a clear pathway. A stimulus triggers an impulsion, that is an urge to act, which can either be successfully inhibited or become an impulse, an action performed without reflection or voluntary direction. What makes impulsivity so significant in mental health research is that its role in primary driver for risky decision making across different domains, whether financial risk like impulsive spending, health risk like dangerous behavior, or social risk like aggressive confrontations. Impulsivity often sits at the core. We can see that developmentally we see fascinating pattern. Adolescents show heightened impulsivity and risk-taking behaviors due to their ongoing brain development, specifically the gap between their rapid developing limbic system, which mostly controls the emotion, and their still maturing prefrontal cortex, that the region of the brain where most of the cognition happens. This imbalance helps explain the peak in risk-taking behavior during teenage years. So most critically for mental health applications, impulsivity traits strongly predict substance abuse, gambling addiction, and other problematic behaviors. This predictive relationship makes impulsivity assessment valuable for early interventions in conditions like ADHD, bipolar disorder, and borderline personality disorder, where impulsivity is often a core symptom. Now, as we understood that emotions, what are emotions, and then we try to understand how we analyze emotions through Russell circumplex model of FI. But now we'll talk about the impulsivity and how impulsivity is essentially quantified. So one of the most widely used assessment tool in both clinical practice and research is the Barat impulsiveness scales of version 11, commonly known as BIS 11. This psychometric instrument uses a simple self-report format where respondents rate the frequency of various impulsivity-related behavior on a 4-point scale, ranging from rarely or never to almost or always. What makes the BIS 11 particularly valuable is its multi-dimensional approach to impulsivity, measuring three distinct impulsivity. First is attentional impulsivity, which represents the inability to focus or concentrate, captured in the statements like I don't pay attention. Then this dimension is particularly relevant for conditions like ADHD and can be exaggerated during depressive episodes. Motor impulsivity involves acting without thinking, reflects in the statements like I act on impulse. This dimension is often elevated in conditions like substance use disorders and bipolar disorder during maniac phases. Non-planning impulsivity reflects a lack of future orientation with the emphasis on present focused thinking captured in the statements like I'm focused on the present. This dimension is frequently implicated in various risk-taking behavior and financial decision-making problems. The total score ranges from 30 to 120, with the higher scores indicating greater impulsivity. Scores above 70 suggest clinical significant impulsivity that may warrant intervention. By providing this nuanced profile of impulsivity, the BIS 11 score helps clinicians target specific dimension for treatment, and it can help researchers to track changes in impulsivity pattern across different mental health conditions. Now coming to the electroencephalography. Electroencephalography, that is EEG, it measures the electrical activity of neurons and is generated by the movement of charged ion across their cell membranes. This slide includes a schematic representation of EEG measurements. EEG provides a direct measure of neural activity, unlike some other brain imaging techniques. As I have already talked, that it offers a very high temporal resolution, allowing for real-time monitoring of brain activity. EEG is non-invasive. It's suitable for a wider range of research and clinical applications, and it can detect subtle changes in brain activity that is associated with different mental state. EEG is particularly useful for studying rapid cognitive process and emotional responses. It is relatively inexpensive compared to another brain imaging techniques, making it widely accessible. Now, we'll understand how we employ EEG to uh, understand and study the emotions and impulsivity. I'll just give you a brief idea about the EEG signal characteristics. Its signal ranges from 1 to 200 microvolts, and the bandwidth is usually 0.5 to 80 hertz. It has a high temporal resolution, and it can exhibit various types of waveforms morphology, such as sharp transients, slow waves, and oscillations. Mainly, it can be filtered into specific frequency ranges, namely delta, which is 1 to 4 hertz, theta, which is 4 to 7 hertz, alpha, which is 8 to 13 hertz, beta, which is 13 to 30 hertz, and gamma, which ranges from greater than 30 hertz. Sometimes there is a higher gamma which is we analyze above 60 hertz, but for the sake of this analysis, we have stick to the frequency levels that is greater than 30 and less than 50 hertz. Now let's talk about emotional analysis using EEG. EEG has significantly evolved over decades. In the 1970s, researchers like Heath primarily relied on visual observation of EEG patterns to study basic emotions, and it lacked quantitative metrics. A breakthrough came in 1985 when Ahern introduced spectral analysis techniques, enabling researchers to quantify EEG signals mathematically and identify frequency-based patterns associated with different emotional states. By 1992, Rochman worked on topographic mapping techniques, revolutionized the field by visualizing the spatial distribution of brain activity during emotional responses, revealing which brain regions activate during which specific emotions. For inducing emotions in laboratory settings, researchers employ various methods like static methods like images to music to cognitive task and questionnaires. However, Hangelak demonstrated in 2005 that audiovisual clips prove particularly effective at generating strong, dynamic, emotional responses that closely mirror the real world experience. Then a source localization done mainly by Jotny and al. In 2007 refined our understanding by identifying specific neural generators that are responsible for emotional processing. Today, advanced EEG signal processing incorporates machine learning algorithms that can detect subtle patterns in the brain activity, enabling more precise classification of emotional states. The recent developments include real-time emotional recognition system and integration with other physiological measures to create comprehensive model of EEG emotional processing. Now talking about impulsivity analysis using EEG, it has revealed a consistent neurological pattern across various populations. One of the most significant findings comes from Ans and colleagues in 2013 on research on ADHD patients that EEG markers are associated with the impulsive behaviors. This evidence base expanded in 2016 when Ras et al. Demonstrated that the reduced alpha power in highly impulsive individuals with gambling disorders and nicotine addictions. This finding suggests that dysregulation in inhibitory control networks. Lee's research in 2017 further identified that there is a damped theta band power specifically in gamblers with high impulsivity, pointing to alterations in cognitive processing and decision-making circuits. And Neil's work from 2017 focused on resting state EEG patterns, which reveals a decreased right frontal alpha activity alongside enhanced beta activity correlating with the trait impulsiveness. This hemispheric specialization suggests that potential biomarkers for impulsivity. And Bath in 2021 did a comprehensive review that synthesized these findings, concluded that alpha, beta, and theta band alterations may manifest differently depending on the specific dimension of impulsivity being examined. A critical limitation of in this field is that most studies have relied on classical statistical approach targeting predetermined EEG features. This methodological constraint has potentially overlooked important spectral or temporal patterns that might better characterize impulsivity. In recent advancements incorporating machine learning may overcome these limitations by identifying complex patterns across multiple frequency bands simultaneously, by offering a more nuanced understanding on the neural basis of impulsivity. So I'll talk about the motivation and aim of the work which I'm going to present. So first, the estimation of information using instrumented approach and explainable AI to understand emotion and impulsivity. Pinpointing electrode and frequency bands in emotion recognition is challenging. Then extraction of biomarkers using advanced nonlinear signal processing techniques that can help to understand complex brain dynamics and neural correlates. And the aim of this work is that analysis and classification of impulsivity and evoke changes in brain regions from audiovisual stimuli in arousal and balance dimensions. Now coming to the methodology, what we employed for the emotion recognition. First, I would like to talk about the database that we have employed. We have employed a deep database, a database of emotional analysis using physiological signals. So this data was recorded from 32 participants. Out of them, 16 were female and 16 were male. The physiological signals that were recorded was EEG and other physiological signals. The instrument that was used was biosemi-active 2 system. The age of the participants were between 19 to 37 years with a mean of 26.9 years. The stimulus type was audiovisual stimuli. The sampling rate at which the data was recorded was 512 hertz, and there were 32 international 1020 system electrodes that were put on these subjects. There were 40 videos that were shown to these subjects, and then they were asked to annotate these audiovisual stimuli based on arousal and balance scale. We can see the way which the signal was recorded is that each subject were given or are shown the audiovisual stimuli in 40 trials. In each trial, they were first shown the trial number, then the fixation cross, which was around 5 seconds, then an audiovisual stimuli for 60 seconds, and then they were asked to self-assess the audiovisual stimuli that they seen, like how much and what exactly they felt. So they were given 2 scales to show or to assess what they felt. So first scale was valence, in which the negativity or positivity of the emotions were quantified. So if the subjects annotated between 1 to 5, it is considered as a low valence. When they annotated between 5 to 9, it is considered as a high valence. Similarly, in the arousal case, where the intensity of the emotions were quantified, when the scale was between 1 to 5, when they annotated between 1 to 5, it is considered as a low arousal, and when they annotated between 5 to 9, it is considered as a high arousal. Then when the 20 videos are showed, they were given a break for some time, and then rest of the 20 videos are shown to these subjects. And then for all 32 subjects, the same process was repeated and the full database was created. So what we did in this analysis is that we took this raw EEG signals in which the audiovisual stimuli was shown to the subjects, and they self-annotated the emotions that they felt. Then the signals was pre-processed with a typical EEG pre-processing pipelines. And then we did a two type of analysis. Once, when we considered each individual electrodes as an individual entity, that is, we considered as a frontal electrodes and then did the analysis. The another analysis we did when we considered all electrodes, we did more interconnected or network-like analysis, in which we assume that whole brain acts as a network and it's not based on the individual entity that is being into play during emotions. So when we considered the frontal electrodes, the rationale behind using a frontal electrodes is that the emotions originates from the subcortical levels of the brain, that is nearby the limbic system, and a complex interplay between limbic system and the amygdala. After it gets originated through the limbic system, which is in the subcortical level of the brain, it comes to the prefrontal cortex. Prefrontal cortex is mostly responsible for the processing of the cognition or the processing of the emotions. So when the emotions originate and it directly goes to the prefrontal cortex, the processing happens. We hypothesize that we can capture these processing of emotions from the prefrontal cortex, and it can be used to identify the state of emotion that is felt, because EEG cannot capture the activity of the subcortical regions of the brain. Now coming to the frontal electrodes, we considered 9 frontal electrodes, that is FP1, AF3, F3, F7, FP2, AF4, FZ, F4 and F8. Then we decomposed each electrode into 4 different frequency bands, that is theta, alpha, beta and gamma. Then what we did is that for each frequency band, we did something called bispectrum analysis. I'll explain about bispectrum more, but as of now, I can explain that we wanted to find out the nonlinear interaction of frequency band in a specific signal, because since human brain is not a linear entity, we all know that a linear entity follows a linear superposition theorem, that whatever the input you give, it follows, the output follows the input. But here when we see brain, it is a non-linear entity, because for example, we see something like a cat, and when we record the EEG signal, we'll not get a similar pattern of cat moving or cat staying or something like that. So the input and output doesn't follow the linear path. So our brain acts as a non-linear entity. So to understand the brain signals, we employed this non-linear technique, that is bispectrum analysis, to understand or relate the EEG signals to the specific emotion state to bind together. So we did the bispectrum analysis and extracted some bispectrum features. So now we have electrodes, frequency band and features. So these are 3 combinations that we try to find out which 3 combinations can better explain the emotions effectively. To find out which of these 3 combinations can predict the emotional state, we used a feature selection algorithm called genetic algorithm. It from using that algorithm, we found out, okay, there is this combination that works better for predicting emotions. Then we use something called explainable AI technique. In this explainable AI technique, we have used 2 types of models, that is glass box models, which is explainable boosting machine, and a black box model like random forest, gradient boosting machine, and extreme gradient boosting. Then we did, after selecting those features, we classified into 2 levels, that is low arousal and high arousal, and low valence and high valence. Then we also explained how this decision was made. Now coming to the second part, where we considered the brain as a network entity, we extracted some indices that are non-linear indices, which we extracted. There are 3 basic indices that we use, that is phase slope index, rho index, and phase locking value. I'll explain about these things in the later part of this presentation. So then what we did is that we took each individual index as a feature, and then we constructed the features from the graph. So when we extract the functional connectivity with between different brain regions, we also extract the we can also extract directly the features, like I'll explain about those features later. Then I have used individually those things to again find out what are the best classification method, and then which frequency bands are better with the which functional connectivity indices can better explain the emotional analysis in the EEG. Now coming to the bispectrum analysis. Bispectrum analysis represents an advanced technique for analyzing nonlinear characteristics in EEG signals that the conventional spectral analysis, that is Fourier transform, often miss. The bispectrum detects the quadratic phase coupling, a phenomena that indicates nonlinear interaction between different frequency components in the brain activity. Quadratic phase coupling manifests when the phases of two frequency components sum together, represented mathematically as F1 and F2. This coupling reveals how different neural oscillations influence each other, potentially offering a greater insights into the brain function than the traditional power spectrum analysis. So, in this, the bispectrum of a discrete signal xn involves taking a one-dimensional Fourier transform of the signal and then computing the formula showed on the slide. In this equation, xf represents the Fourier transform of the discrete signal. F1 and F2 are the frequency indices we are examining. X star denotes the complex conjugate. The visualization on the right hand side demonstrate what actually the bispectral data look like. The upper image shows a normalized bispectrum across the 4 to 45 hertz range, while these more zoomed over image, that is lower image, focuses on the 8 to 12 hertz of frequency range. The alpha band activity that is particularly relevant to the uh, emotion analysis, the bright spots represent different regions of strong phase coupling between different frequency bands. This is especially valuable for this work because nonlinear dynamics in the brain signals, as I have talked about, may contain critical information about the emotional state that would remain hidden when using a linear analysis methods like traditional Fourier transform. Now coming to the features that we have extracted. So after we get the bispectrum from the signal, we take the principal domain, that is ohm, of the non-redundant region of the bispectrum. You can see on the right bottom of the screen that if you take the bottom or principal domain, which is non-redundant region, it is enough to explain the bispectrum. Otherwise, it is just a mirror image on the line y equal to x and line y equal to minus x. So it's just a mirror image of it. So for all the analysis, we took the principal domain of the non-redundant region and extracted the typical bispectral features like normalized bispectral entropy, normalized square bispectral entropy, moment of the bispectrum, mean magnitude of the bispectrum, bispectrum variance, sum of logarithmic amplitudes, sum of in the diagonal elements of bispectrum, first order spectral moment. Okay, now after that, I'm going to talk about the functional connectivity measures. As I've already talked about that, I have used three different functional connectivity measures. First is the phase lag index. Excuse me. The first one is phase lag index. It evaluates the sign of phase disparities across all feasible channel pairing. Phi mk and phi nk represent the phase difference between the electrode signal m and the electrode signal n at time t. K is the length of the time series and j is the imaginary part of the unit. Then phase locking value, it assesses the magnitude of the average phase disparity between pairs of signals. Then the rho index, which is not well applied into this method, into this field, it measures the synchrony that uses Shannon entropy to quantify the deviation of the underlying relative phase from a uniformly distributed phase, where SE max is the highest entropy that can be achieved by uniform distribution divided into Q equal bins, and S is the entropy of the relative phase, that is phi relative with the phase in the signal M, that is electrode M, and the phase in the signal N. So how do we read this functional connectivity matrix? So if we see this functional connectivity matrix, it consists of 32 EG electrodes on both the sides. We can see that it is a symmetric matrix, means the lower triangle of a matrix is symmetric to the upper triangular of the matrix. So what it shows, we can see in this functional connectivity matrix, it shows that at each intersection, for example, OZ, if we see the intersection or interaction of OZ with the P4 or we can see in the P4, the interaction is relatively less. That is, we can see from the strength of the connectivity, or the bar or the color bar shows how much they are related. Means if it is phase slope index, how the slope of a phase is changing, or phase lag index means if the first signal is this, the second signal is this, how the phase is lagging from the first signal. That's how we try to read the functional connectivity matrix. Now coming to the functional connectivity features. So as I've already explained, we used the two types of functional connectivity features. One, we constructed the graph out of the functional connectivity matrix. We can see that in the node I connections and the node J connections, we take each weight and put into the connection between those two nodes. So this is one node and two node, and the connection between them, that is color, we put as a weight between these two nodes. And then when we use all the nodes and all the edges, all the nodes and all the edges, we extract the features from the network. We have extracted mainly 5 features, that is characteristic path length, average clustering coefficient, network efficiency, node degree, and eigenvector centrality. So what characteristic path length tells us, it's a topological measure that calculates the average minimum number of edges needed to travel from one node to another in a network. The average clustering coefficient is a global measure of network segregation, means how well the network is segregated. It is calculated by averaging the clustering coefficient of all the nodes in a network. The global efficiency of a network or the network efficiency of a network is defined as the average of inverse distance between all pairs of vertices. The degree of node is the number of edges or links connected to a node. Eigenvector centrality is a graph theory algorithm that measures the influence of a node in a network. It considers the importance of a node neighbors. The second way that we did is that we directly use the connectivity matrix as a feature. So what we did is that we took the upper triangular matrix, stripped each row apart, and then stacked together to create a one-dimensional feature set. By stacking these features, we have more number of features in this, and then we use directly these features to classify the emotional states. Now I'll talk a little bit about methodology in impulsivity. So as I have told that we have considered one specific database for the emotional analysis. For the impulsivity, we essentially recorded the signal from the subjects. So what we did is that we used brain amp MR amplifier to record the EEG signals, and here we used 56 participants, in which 19 were female and 37 were male. Their age was around 21 years with a standard deviation of half a year. The stimulus type was risk into reward. I'll talk about a little bit in a second. Then the sampling rate was 256 hertz, and there were 62 EEG electrodes for the international 1020 systems. And then there were total 80 stimulus. And then before recording the signal, we asked the subjects to fill the BIS 11 form. With that, we have estimated their impulsivity levels into low, mid, and high. So what we did is that we used a EEG BART paradigm. In this paradigm, we tell the subjects that if a balloon is growing, and if they and a balloon is growing until it bursts out. If you cash the money before the balloon bursts out, you get more money. So if the balloon bursts out, they lose everything. And if the balloon size is low and they cash out, they get the less money. So you see, we are trying to induce an impulsive reaction from the subjects so that we can understand or activate the part of the brain which is responsible for the impulsivity, so that we can use those EEG signal and quantify the impulsivity from the neural correlates of this in EEG. So yeah, we performed the BART paradigm for 6,000 milliseconds, that is 6 seconds. And then we asked the subjects to cash out. Then we did the 62 electrode implantation on the subjects. Then we did a basic pre-processing pipelines. We did artifact correction. We did specific bandpass filtering, segmentation, and then referencing. We have estimated only one feature in this analysis, that is average power from 62 electrodes. Then we used 4 types of classification algorithms, that is support vector machines, k nearest neighbors, linear discriminant analysis, random forest, the very traditional machine learning algorithm. Then what we did is that we tried to find out which frequency band is best performing among all frequency bands. Then we did an electrode selection. using a algorithm called sequential bidirectional feature selection. What it does is that it takes a best performing feature and then tries to find out the other best performing features. If the other feature performs good, it adds it, otherwise it's remove it. Then finally, we did two types of analysis, that is statistical analysis and a sharp analysis, which is essentially an explainable AI. So we can see that these paradigm is mainly for to stimulate the effect of impulsivity into the subjects. Now coming finally to the classification, as I have already told, we have used some types of black box classifiers like KNN, random forest, support vector machine, and extreme gradient boosting machine. And then we have used a glass box classifier like explainable boosting machine. So it's a traditional classifier which is already a transparent classifier that combines gradient boosting, and it mostly focuses on interpretability. And boosting is a method used in machine learning to reduce errors in the predictive data analysis. Gradient boosting is a supervised machine learning algorithm that combines the estimates of a set of simple, weaker model to accurately predict the target variable. Then the other type of analysis that we did is that SHAP analysis. SHAP analysis converts the existing black box model into a glass box models. Then for all the analysis, we have used a leave one subject out cross validation for validating the performance to check the robustness and generalizability of the proposed approach. And then we have used accuracy, precision, recall, F measure to evaluate the performance of the trained classifiers. Now coming to the results of the signal. First, I'll show the basic, I'm showing the basic representative EEG signals. It consists of 32 subjects. This is the signal for the emotional analysis. There were 32 subjects, 40 videos, 32 electrodes. Then duration of each signal was 60 seconds. And the sampling rate, we downsampled from 512 hertz to 128 hertz because our area or our frequency of interest was maximum of 64 hertz. Then there were 1,280 number of instances, that is 32 subjects and 40 videos. There are a total of 40,960 EEG signals, that is 32 subjects, 32 electrodes, and 40 videos, which in turn makes the total duration of signals as 2.4 million seconds, which is around 683 hours. So we processed the 683 hours of data to try to understand this relationship of emotions with the EEG signal. Now, just to show that two frontal electrodes F3 and F4 and their respective EEG signals, and we can see that for a specific emotions, we see a difference in both F3 and F4. I mean, this is the instance when the subject was shown the audiovisual stimuli. We see that there is a subtle difference between F3 and F4, specifically in the amplitude, but this was not translated throughout the subjects and throughout the videos. We decompose the signal into 4 frequency bands, that is theta, alpha, beta, and gamma, which is already shown in the right lower part of the slide. Now let's talk about the bispectrum of EEG signals. This is the plot I've already talked about, like how the bright areas show that there is a high nonlinear coupling between 8 to 12 hertz frequency range, that the frequency during these ranges gets coupled together and form a nonlinear relationship between them during a specific emotional states. What are those specific emotional states? We can see on the right hand side of the plot. You can see that in the F3 electrode, the low arousal and high arousal, you can see a more yellow or red areas in high arousal F3 electrode as compared to low arousal F3 electrode. Similar pattern was seen in the F7 electrodes for low valence and high valence, that we see that more interaction or more coupling is seen in the high valence state in the F7 electrode as compared to low valence state in the F7 electrode. Now we took those features and put it into the classifiers, and we found out that for arousal, the gamma band and the explainable boosting machine outperformed the other classifiers, whereas during valence, the alpha band with the explainable boosting machine outperformed the other classifier. Moreover, the performance of the other frequency band are not very low as compared to the better performing frequency band. So we cannot say like only single frequency band can be enough to understand the emotions in the EEG. So what we did is that we combined all of them and tried to find out which frequency band and which electrodes get selected in the final classification model. We found out that in theta band, most of the right side, frontal right side of the electrode gets selected for the arousal case, as but in the left hand side, the valence state electrodes are selected. But this was not seen in other frequency bands, because there was a mix of both arousal electrodes and valence electrodes left and right, and the midline. Only one single electrode was selected for the same feature, for the same for both arousal and valence, that was F4 for the bispectral entropy. Otherwise both the valence and arousal was selected differently. So with this, we can also say that the valence and arousal are orthogonal, and different frequency regions and different electrodes are mostly involved in the analysis or processing of these emotions. Now coming to the explainability of arousal emotions, we found out that, okay, not a single feature or not a single electrode or frequency band is especially important. Rather, a combination of all these are important in predicting the emotions. We can see the probability occurrence plot. We can see that that probability of occurrence in a low arousal state is more when the feature that is shown in the bottom, it is SSM diagonal in theta band. For the FZ electrodes, when the values are low, the more chances of occurrence of low arousal is there. When you see the dark patches, am I audible?
Yes, sir. Yes.
Okay, yeah. So I was talking about the explainability in the arousal case. So I was talking about that these dark patches shows that when the value on these in the range of these values were high, then there are more chances that the specific emotional state is the high arousal. So it shows that the specific feature, rather the combination of features, can be more useful to predict the specific emotional state. Now coming to the valence, we saw the similar pattern that was found in the arousal as well. So not a specific feature frequency band or electrode. Rather, the combination of this works best to understand the emotions or to predict the emotions effectively. Now coming to the second part of the analysis, that was brain networks that was used to predict the arousal and valence. We can see all these three networks for different the emotional states. We found that there were differences in these network patterns, but to quantify this, we use those direct features, as a feature, and directly and extracting the network features from them. Then we tried to show, we saw that there are some significant connections that was found in these frequency in these the connections in different frequency bands. We found out that the rho and PLV showed more significant connections as compared to PLI in most of the frequency bands, specifically in the alpha, beta, and theta band. Now, when we put directly index as a feature, we found out that gamma band for both arousal and valence, and rho index performed best in differentiating low arousal and high arousal, and low valence and high valence. And when we extracted graph-based network features, we found that the random forest performed better in discriminating the levels of arousal and valence. But if we compare directly, like directly index as a feature and graph-based network as a feature, we found out that if we directly put the index as a feature, we get a better performance in estimating the levels of arousal and valence. Now coming to the impulsivity analysis, this is the representative EEG of EEG and the brain max that is associated with three levels of impulsivity, that is low impulsivity, mid impulsivity, and high impulsivity. We see that in the prefrontal region, that is FP1, we see some visual differences in the signals in these three different impulsivity subjects. but that is for the FP1 electrode. But for the other electrodes in the brain maps, we can see that the power of the all the electrodes, when we plot on the brain maps, we see the differences as well, specifically in the parietal region and the frontal region of the brain. You see that in the P1, PZ, P2, and POZ that are consistently different in all three impulsivity states. As I've already told that I've used directly power as a feature extracted from different frequency bands, and then I have put all the features from all the electrodes into classifiers and found out that random forest classifier in the alpha band performs best in discriminating the levels of impulsivity. Then theta band and theta, beta, and gamma bands perform similar. It's not like that they are performing really bad to it. Now coming to the electrode selection, now we know that the alpha band performs best in discriminating the levels of impulsivity. We try to find out which specific electrodes are responsible for the impulsivity prediction. We did a sequential bidirectional feature selection in which if the electrode is performing good, we kept adding. If it is performing bad, we kept on removing. And we found out that only 10 electrodes are enough to classify the levels of impulsivity with a F measure of 94.5%. As you can see in the plot that after selecting the 10 features, the performance was not improving significantly. So we found out that 10 electrodes are enough to classify the levels of impulsivity. Now, based on the relevant electrodes that were then we chose specific electrodes in the specific frequency band, and we found out that when we choose these electrodes, the map of the brain shows in different frequency bands for different impulsivity as different. Mainly in the frontal regions and the parietal regions show the differences. Moreover, if we see in the gamma band, you see that the midline of the brain is mostly involved in the impulsivity prediction. Now coming to the explanation of the impulsivity groups, as I've already told that I have used the SHAP analysis in the random forest classifier to find out how the impulsivity is predicted. I mean, what classifier sees that it puts the specific case as high impulsivity, low impulsivity, and mid impulsivity. We found out that the FC2 electrode, POZ electrode, and CP2 electrodes are essentially mostly responsible for impulsivity classification in all the cases, that is low, mid, and high impulsivity. I would like to explain this sharp B-swarm plot. This is a very interesting plot. You can see, for example, in the low impulsivity group, we can see that the FC2 electrode, if the values of the so if it is on the right hand side, there are more chances that is into the group that is in the low impulsivity group, and if it is left hand of the side, it means that there are high chances it is in the non-low impulsivity group. So if the values of the FC2 power is high, then it is more chance that it is a low impulsivity group. Similarly, if we see in the mid impulsivity group, that if the values are low, that is, it is on the right hand side, the values are low, there is a high chances that it is the low mid impulsivity group. And if the values are high, then it is more chances that it is not in a mid impulsivity group, which we can see similarly in the high impulsivity group. So if FC2 values, which we see on the first group, that is low impulsivity group, if the values are low, then it is high chance that it is not in the high impulsivity group. But if the values are high, then it is high chance that it is not in this group. So, I mean, the combination of the values plotted on this B-swarm plot explains how the classifier decides which frequency, which feature yields which classes, and combination of these also tells that how feature is distributed in these different classes. Now, then what we did is that we tried to find out what is the important feature or important electrode in specific frequency band in predicting a specific impulsivity. So we did a 1 versus rest feature selection for individual impulsivity level using absolute power from the individual frequency band. And then we found out that the POZ and FPZ and CPZ, all midline electrodes, were selected most consistently to predict the levels of the impulsivity. With this, we can easily conclude that midline electrodes, that is FPZ, POZ, and CPZ, are essential to predict the levels of impulsivity from EEG. Now, this plot also shows the relevant electrodes and their feature importance. It also shows that in most of the cases, the POZ is relatively more important in most of the cases, and PZ, CPZ. So the left and right electrodes, apart from the temporal ones, are not essentially more important in most of the cases for predicting the impulsivity levels. Now, I would like to conclude and talk about my final thoughts. First of all, EEG effectively captures emotional and impulsive responses and offers a non-invasive approach to understand brain dynamics. The alpha band shows the highest classification accuracy for detecting emotions and impulsivity. Functional connectivity measures, including the row index, provides insight into neural synchronization. Random forest, EPM, and XGBoost achieved high accuracy with sharp enhancing feature interpretability. Then selecting 10 key electrodes reduce the data complexity while maintaining classification accuracy. And then integrating findings into AI system can enable early diagnosis and personalized mental health treatment. There are other works that I were carrying out using deep learning techniques. In this, I've simply used the time frequency plots and super resolution time frequency plots and used a self-attention convolutional layer to predict the high valence to low valence. And then I've also used the multi-scale CNN to see the information of emotions into the specific scale of EEG, and then exploiting that to classify into levels of arousal and balance. Then this is one another work which we did using fMRI signals to see whether the similar pattern of brain we can find it in fMRI for the prediction of impulsivity. Here we did do the classification, rather we were trying to predict the exact level of impulsivity. We have used some similar techniques and used exactly the index as a feature to predict the levels of impulsivity. We have found out that index as a feature is enough to classify into different levels of impulsivity, but here we use the level of the regression problem. Then these are the references that I have used. Finally, I want to acknowledge some people. First of all, Professor S. Ramakrishnan, my supervisor at IIT Madras. Then Dr. Nagarajan, that he was the postdoc that helped me during my PhD. My co-supervisor, Dr. Subham, she's from NIT Calicut. My German supervisor, Professor Uta Habel. But the postdoc in the Professor Uta Habel's lab, Dr. Philippa, and most importantly, Indian Institute of Technology, IIT Madras. Then faculty, office, and laboratory staff of Department of Applied Mechanics and Biomedical Engineering. Then obviously Ministry of Education, Government of India, for providing me the fellowship for traveling for conferences and for pursuing out my research. Then I would like to thank Uniclinic RWTH Aachen, Germany, for providing me the stay to work on the research work. And then finally DARD, which is a German federal office organization, that is government of Germany. Thank you. If you have any questions, you can just mail me or just thank you. Thanks a lot for your time.
Thank you, sir. It has been a truly wonderful session. I would like to add that Shubha DP was also my research guide at NIT Calicut. So the class was very descriptive. I would like to know if there is any queries from the participants. Okay, sir, there is one thing I would like to ask. So for developing this, it's a very simple question actually. For developing
sure, go ahead.
for developing graph from connectivity metrics, what is the approach that you've used? Whether it's like directly thresholding method, or is there any strategy for that?
Yes. So as I've explained that I've used two methods. First, I've viewed directly as a feature. So there I didn't do any thresholding. So whatever the feature I got, I just stripped into a single 1D vector and made it as a feature. The second thing what we did is that we extracted features from the networks that we constructed. So network construction we did, and we did it, provided a threshold of 0.8. So if the connectivity is greater than 0.8, we consider it as a connectivity and weight of that. So 0.8 to 1, I have weighted it, and above that I've considered. Below whatever we are getting, we have just excluded it. So after that, we have used spectral graph theory and all those features and lot of stuff there. I didn't go into detail, but if you want, I can just explain it to you.
Okay, sir. Thank you. So the session was interesting by providing a very good understanding on emotions, its complexity, its quantification, and the impulsivity analysis with EEG. So the results also described multiple parameters to analyze the emotional state. It is truly motivating, and definitely hope that the participants will use this understanding in their research and future projects. I would like to thank behalf of all the participants and the Electronics and Biomedical Department from the Adi Shankara Institute of Engineering and Technology for the wonderful session. Thank you, sir.
Thank you, Surya, and thank you all of you for listening to me for 1 hour. Thanks a lot.
Okay. I also want to thank all the participants who have joined for the session. Thank you all. Have a good day.
Thank you. Bye bye.